Welcome to our video on polar coordinates and equations. So let's define what we mean by the polar coordinate system. So looking at this picture right here, I've got several things going on here. I've got my Cartesian coordinate system, x, y, and then on top of that, I'm going to show you how the polar coordinate system works. First of all, a few definitions. The pole is considered the point 0, 0, which is the same place as what we call the origin in the Cartesian coordinate system. So we call that the pole in the polar coordinate system. Then we have the polar axis, which is a ray with an end point 0, 0, extending in the positive x direction. So my polar axis is this ray starting here and going this way to infinity. Polar axis. All right. A point r theta is an ordered pair in polar coordinates, just like in Cartesian coordinates, the point xy is an ordered pair. So you have two coordinates, the r coordinate and the theta coordinate. So if I look over here in my picture, this is my pole. My r coordinate is the distance out to my point from the pole. So this is my r. So that's my first coordinate, the distance from the pole out to my point. My second coordinate, which is theta, is the rotation from starting at the polar axis, going positive in the counterclockwise direction. So this here is your positive theta in this diagram, and that's your second coordinate. So each point is defined by its radial location r from the pole and its angular rotation from the polar axis in the positive direction being counterclockwise. Now this is a little different here. R can take on a negative value in polar coordinates, and what that means, let's just try to describe that as briefly as possible because we'll get into some examples in a minute on that. So what we mean by a negative radius is if I was starting at my pole here and I went this way, this same amount r, and hit this point over here, this would be my point negative r theta. So this is r theta, where I went along my theta line right here. This is my theta line out to here in a positive direction here, and then backwards from this pole in a negative direction here. This is what we call a negative r with the same theta, this one. All right, so we're going to get into this a little bit further in some of our examples. So this is how a piece of graph paper or your on the Desmos graphing calculator online that I showed you in the other video. This is how your coordinate system would look on paper. So you'll usually see some radial lines. Sometimes they'll be divided into twelfths, sometimes sixths. So this one has every 12th here, 1/12, 2/12, 3/12, 4/12, etc., all the way around 360 degrees or 2 pi radians. So we're going to work mostly in radians, but you can also see this graph paper, so to speak, with degree marks along the outside here instead. All right, and then this would be a radius of 1, radius of 2, radius of 3. So they'll be marked 1, 2, 3, 4, or 2, 4, 6, 8, however your graph is. All right, so this is how we can plot a point on a piece of graph paper. So a point right here is going to have an r. So in this case it's 4, and it's going to have a theta. In this case it's pi over 6. Okay, so in this example, let's just plot these 2 points. The first one is 2 and the angle theta. So this is 2. Let's just mark it up a little here. This is my r. This is my theta. All right, so theta is going to go this way, positive. All right, so my r is 2 and my theta is 3 pi over 4. So on my 2 radial line, I'm going to rotate around. Let's find 3 pi over 4, and I'm going to plot my point there. Alright, so this is my theta here, and this is my r here. Okay, so this is my point here, 2, 3 pi over 4. Alright, so let's do the other one. Let's do it in a different color. So this is my r and my theta. So now I'm on my 3 radial line, and I'm going to go in the negative direction, 1/6. And I'm going to put my point right here. So this is my theta, which is, in this case, negative pi over 6. And then this is my radial distance r, which is 3. And this is my point. Next, let's take a look at these 2 points here. So I'm going to plot 4 pi over 3. So that's a radius of 4 and a rotation of pi over 3. So 4, I'm on this line out to here. Alright, so here's my point here. Alright, so that's point A. Let's just call that A. And we'll call this one B. Alright, now we've got negative 4 pi over 3. Alright, so we've got a negative radius. So let's go ahead and find 4 pi over 3 first. So that's this radial line here. Alright, so I want to extend that radial line in the other direction because I'm going to have to go negative if I have a negative r. Alright, so if I start at my pole along this radial line, alright, so this is 4 pi over 3 starting at my initial side all the way around to here. That amount of rotation. However, if I want to get a negative r in there, I'm going to have to go backwards along this line here, which I extend backwards. Alright, so if I go backwards 4 from the pole, you're going to find that A and B are the same point. This point and this point are exactly in the same location on my graph. Alright, so that can happen with points in polar coordinates. Okay, one more point let's do. I'm going to plot this point, call it C, negative 1.5, negative 5 pi over 3. So that means I'm going to have to rotate in the negative direction, 5 pi over 3. So in order to figure out where I am with this, I'm going to divide my circle into thirds. Alright, so I'm going to draw this line. So I've got 1/3. So every 4 markings I've got a third line, 2/3, 3/3, 4/3, 5/3. Alright, so if I go in the negative direction, negative 5/3, I'm going to be here. This would be 1, 2, 3, 4, 5. Okay, so that's going to be my angle, negative 5 pi over 3. So I'm on this line here, starting at my pole. Alright, and then I have to go negative r here. So I'm going to extend my line, just make it dotted here, this way, and then I'll go 1.5 from the pole, which will put me right here. So this will be my point C. So that's a point that had a negative in the r direction and a negative in the theta direction as well. The next thing we learn how to do is convert between polar and Cartesian coordinates. So what we can see from this diagram here is that if this is your pole right here, and this is your polar axis, and this is theta in the positive direction out to this radial line right here. This point right here can be thought of as having the polar coordinates are theta and the Cartesian coordinates x and y. So both of these coordinate systems describe this point here. So we're going to learn how to turn this into this or turn this into this, because after all, they describe the same point, just in a different way. All right, so when we talk about an angle theta and its initial side is the polar axis and it's defined in the positive direction this way, we know that the reference angle right here for this triangle over here is going to be that theta there. All right, where it's just call this one theta 1, where theta is equal to the angle that this radial line here makes with the x-axis. Okay, so we already know that about reference angles from our prior studies. And so you can see that theta plus theta 1 are going to equal 180 in this particular case. But anyway, the reference angle is the angle that you make with the x-axis when you drop your perpendicular. All right, and that's how we developed. Let's just erase that. All right, that's how we can say that the trig functions of this angle here are equal to the trig functions of this angle here. So we know, let's look at this one here. The cosine of this angle theta is equal to adjacent over hypotenuse. If I multiply both sides by r, I have x is equal to r cosine of theta. I know that the sine of theta is opposite over hypotenuse, and that y must be equal to, if I multiply both sides by r times the sine of theta. I also know that the tangent of theta is equal to opposite over adjacent, and I use that to find my angle theta when I'm converting from Cartesian to polar coordinates. If I take the inverse tangent of both sides, I get theta is equal to this, inverse tangent of y over x. I also have the Pythagorean theorem for this triangle here. R squared is equal to x squared plus y squared. So this allows me to form a relationship between y, x, and r. Okay, so this is an important note here, and when we're trying to find our angle theta, so we would take the inverse tangent of y over x, our reference angle. Now, because we had to put domain restrictions and range restrictions, so to speak, on our inverse trig functions, the range of our inverse tangent function is restricted to negative pi over 2 to pi over 2. So this is the range of your inverse tangent function. So it won't give you an angle in these two quadrants over here. So you have to know where your point lies and which quadrant it lies when you do your angle. All right, so what's going on is, let's take, for instance, this point over here. That point is going to have the same tangent as this point over here in Q4. So those two points are 180 degrees apart. They're going to have the same tangent. All right, and then if you look at Q1 and Q3, 2 points that are 180 degrees apart, one in Q1 and one in Q3, those 2 points will also have the same tangent. So your inverse tangent function will only give you either this value or this value. So you would have to know whether you're in one of the other two quadrants to make sure that you were able to define your angle theta properly when you were converting to polar coordinates. All right, so we're going to have to practice some of that in some of the other examples. Okay, in this first example, we're going to convert 2 points to Cartesian coordinates. So our relationships are as follows. So these are our relationships between all of our coordinates in Cartesian and polar coordinates. So we're given polar coordinates here, and we're going to convert to Cartesian coordinates. So looking at the first one, if we have the point 6 pi over 6, r is 6, and theta is pi over 6. So if I want to calculate my x-coordinate, I would say x is equal to r cosine of theta. Right, so theta being pi over 6 is right here. So I know my x is my cosine, root 3 over 2. And my y is my sine, 1/2 from my unit circle. So I can say my x-coordinate is equal to 6 times the cosine of theta, which is root 3 over 2. So x is equal to 3 root 3 if I reduce 6 over 2. All right, now I can say that my y-coordinate is equal to r sine of theta. Y is equal to 6 times the sine of theta, which is 1/2. So y is equal to 3. So my point in Cartesian coordinates is 3 root 3, 3. So this is my Cartesian coordinates. So I converted from polar coordinates to Cartesian coordinates. All right, now I have the point r theta. R is 7, theta is 5 pi over 6, which would be over here in the second quadrant. So cosine would be negative root 3 over 2, and sine would be 1/2. So my x is equal to r cosine of theta. So x is equal to 7 times root 3 over 2. So that's equal to 7 root 3 over 2. All right, that's a negative actually, so we've got a negative in here. Okay, and then y is equal to r sine of theta, which is equal to 7 times 1/2. So y is equal to 7 over 2. So my Cartesian coordinates are x, that, y, that. And we leave it in what we call exact form. All right, instead of converting those to decimal numbers. All right, so that's exact form. Okay, next we're going to start out with Cartesian coordinates, x, y, and we're going to convert to r theta. Once again, we need our relationships. So we've also got theta is equal to the inverse tangent of y over x. All right? So first let's find r. So we're going to use the relationship r squared is equal to x squared plus y squared. R squared is equal to negative 2 squared plus negative 3 squared. So that's 4 plus 9 is 13. So r is equal to root 13. All right, so next we're going to find theta. Theta is equal to the inverse tangent of y over x. So that's the inverse tangent of 3/2. So I'm going to type that into my calculator, and in radians I get 0.982794. All right, now let's look at our drawing to make sure that we're in the correct quadrant with theta here, because this is what we have to be careful about when we're doing inverse tangents. All right, so I've got negative 2, negative 3, so I'm in this quadrant over here. All right, and I found out, according to my calculator, that theta is 0.98274 radians. All right, remember, this is 3.14 radians, this is 1.57 radians, which is half of pi. All right, so this number right here is in Q1, whereas my number is in Q3. All right. So this is what I'm talking about. Along this radial line here, your calculator gave you 0.982794, but we have to realize is that that dimension right there is that same amount. So my real theta is going to be starting at my initial side over to here. My real theta is going to equal to pi from here to here, and then 0.982794 added to pi. All right, and this is pretty much the only tricky thing in this business here is deciding which quadrant you're in. And I know I'm in the third quadrant because I have negative x and negative y. So this value right here that my calculator gives me for inverse tangent is the Q1 value, and I need to add pi to it to get my Q3 value. Okay, so when I add pi to it, I get 4.1244 radians. So my point then, my final answer is my coordinate pair r theta is equal to root 13, comma 4.1244 radians. This is my answer, my r theta. All right, let's do the other point. So we've got the point 4, -2. So let's see what quadrant we're in here. So positive x, negative y. All right, so I'm over here. So this is going to be my r, and this is going to be my theta. Okay, so first let's find r. So I know r squared is equal to x squared plus y squared. So I've got 4 squared plus -2 squared. So that's 16 plus 4, which is 20. So the square root of 20 is equal to 2 square roots of 5. All right, so this is my r. So next I'm going to find theta, which is equal to the inverse tangent of y over x. So we can just leave it like that instead of making it -1/2. So in radians in my calculator, I got -0.463648. Okay, so that means that it gave me this amount right here. Okay, so that's -0.63 blah blah blah. All right, so if I want that theta from my, let's fix this here. This should off the line a little bit. If I want that theta from my initial side here, it's got to rotate all the way around here, starting at here, going all the way around to here. So that's going to be 2 pi taking away this little negative angle here in that quadrant, in this quadrant here, in the fourth quadrant. Okay, so I'm going to say theta equals 2 pi minus 0.463648. So I got 5.6395 radians. So that's definitely in Q4 because 2 pi radians over here is 6.28. This is 4.71. Okay, so now if I write my final form of my point, r theta, I've got r is equal to 2 root 5, and theta is equal to 5.6395 radians. Okay, next we're going to convert equations to polar form. So I've got an equation here that says x is equal to -4. So I'm going to use this relationship here which says r cosine of theta is equal to -4. So the way that we write polar equations is we write r as a function of theta. It's similar to how we say f as a function of x. All right, so you want your r on the left and anything with theta on the right. Okay, so here's my r. So I'm going to get rid of this theta here. So let's just call that solve for r. This is like we solve for y, right? Okay, so solve for r like we solve for y in Cartesian coordinates. All right, so in order to do that, I'm going to divide by the cosine of theta. What you do to the left, you do to the right. So I'm going to have r of theta now. It's going to be my r equation is -4 over the cosine of theta. All right, so that's all there is to it. So what this actually would look like, the equation x is equal to -4 is a vertical line. So this right here is a vertical line in polar coordinates. All right, let's do the other one. So my second equation that I'm looking for, let's do y is equal to x. So I'm trying to write it in polar form, so I'm going to use y is equal to r sine of theta, and I'm going to substitute r sine of theta for y. So r sine of theta for y is equal to 6. Now I'm going to solve for r, just like we solve for y in Cartesian coordinates. So I've got 6 divided by the sine of theta. All right, so this is r of theta. So what this would look like, y is equal to 6. Y is equal to 6 is a horizontal line. So this is an equation of a horizontal line in polar coordinates. Next, we're going to convert from polar coordinates, these equations, to Cartesian coordinates. So we're going to go in the other direction now. So we've got an r and a theta, and we want to change to x and y. So we start out by saying if we have r is equal to 6 sine of theta, we want to introduce an r into the equation here so that we have an r squared and so that we have an r sine of theta. So what you simply do is a sort of like a trick that you would want to know of ahead of time, is you multiply both sides by r. So I've got r squared, let's just call this 6r instead of r6 sine of theta. Okay, so now we know right here we have y from this relationship. And over here we know we have x squared plus y squared from this relationship. So let's substitute x squared plus y squared for r squared and substitute y for r sine of theta. All right, now from conics we know that this is an equation of some sort of conic. So it's got a plus in the middle here, and it's got a 1 in front of the x squared and the 1 in front of the y squared. This is actually a circle, okay, with a y offset here, okay? So it's a circle that's going to be, it's going to have its center moved in the y direction. All right, so this is, we'll just stop there. We don't have to go ahead and solve for y. We're just going to leave it in general conics form. So this is our equation of a circle, and we're going to leave it in general conics form. All right, so let's do the second one. So we've got this equation that we're going to convert to x and y. So we're going to do the same trick, so to speak, to get this r squared here and to get this r in here. We're going to multiply both sides by r. So you might want to make a note of that beside your work in your notes. That's what we're going to do. We're going to multiply both sides by r. So we've got r squared is equal to negative 3r cosine of theta. Now we're going to substitute for r squared, knowing that r squared is x squared plus y squared. We also know that r cosine of theta is equal to x. All right, so once again, we have general conics form of a circle. Okay, this one, the y-coordinate is 0 for the center, and the x-coordinate is offset in this particular problem here. Okay, so this is a circle. All right, and it's going to look something like this. Okay. All right, so now we've got this equation. R is equal to some function of theta. This is r of theta. And we want to convert it to Cartesian form. So an equation in terms of x and y. All right, so let's write it down. All right, and then what I'm going to do is I'm going to put a 1 under here. And I'm going to cross multiply. I'm going to say that r times 11 sine theta plus 6 cosine theta is equal to 22 times 1. All right, so that's equal to 11r sine theta plus 6r cosine theta, which is equal to 22. So then I want to substitute for r sine theta and r cosine theta. R sine theta is y, and r cosine theta is x. So that's 11y plus 6x is equal to 22. All right, so let's solve for y, because this one's a line, and we'll get it in the form y is equal to mx plus b. All right, so 11y is equal to negative 6x plus 22. So that means y is equal to negative 6 over 11x plus 22 over 11, which that one would reduce. So let's reduce that fraction plus 2. All right, so this is y is equal to mx plus b. This is a line. So in polar coordinates, a line, a linear equation would look like this, or in Cartesian coordinates, it would look like this. All right, in this equation, we're going to polar form, so that means we want to solve for r of theta. So we want to isolate r of theta on the left-hand side, and whatever else would be on the right-hand side. So the first thing I'm going to do is substitute for y on the left, r sine of theta, and x on the right, x is r cosine of theta. And I want to solve this for r. All right, so let's go ahead and multiply everything by 3 to clear the fraction. So that would be 3r sine of theta. Let's write it up here. I'm multiplying everything by 3 is equal to negative 2r cosine of theta plus 15. Okay, so I just multiplied everything through by 3, which is this denominator, to get that to cancel out. So 3r sine theta, then this 3 here would cancel with this 3 here, negative 2r cosine theta. 3 times 5 is 15. All right, now let's bring all of the r terms to the right-hand side, to the left-hand side. So we'll have 3r sine theta plus 2r cosine of theta is equal to 15. And let's factor out an r here. So I have 3 sine of theta plus 2 cosine of theta is equal to 15. Right, so I've almost got r isolated here. Just divide by 3 sine theta plus 2 cosine of theta on both sides. And now I have r is equal to 15 in the numerator and 3 sine of theta plus 2 cosine of theta in the denominator. So this is your r of theta. All right, so we've got it in the form of r of theta, and this is your, remember on the last slide we went from looking like this to looking like this. So a polar form of a linear equation to Cartesian form of a linear equation, and then we went from Cartesian to polar. Okay, the last thing I'm going to do here is I'm going to write the polar equation for this red circle here. So I've got a circle graphed on this graph paper here. So this is actually a very simple equation, and the way you interpret this is that no matter what theta is, r is always going to be the same number. See, this is a 5 here, so this is 1, 2, 3, 4, 5. So this is a radius of 3. This circle here is a radius of 3. In fact, we just say our equation, r of theta, is equal to 3. Okay, so this is equation of a circle with a center right here at the origin or at the pole. So a circle has a very simple equation in terms of polar coordinates. And their interpretation of that is no matter what the theta is, r is always going to be 3. All right, so that wraps up everything that we're going to do in this section where we learned about polar coordinates and converting between polar and Cartesian coordinate systems. All right, go ahead and give your homework problems a try and let me know if you run into any questions. One more thing, I just want to add a footnote to this video. In proof reading this video, I noticed I used the word functions just by force of habit. So these really aren't functions when we talk about things that are like circles. They wouldn't pass the vertical line test. So what we really should say is that these are equations.